Hello everyone, this is Engineer Salas from Yellow Academy and Brain Boosters, and today we are going to discuss about chapter 28, and we need a source code as well. You can download it from the website and you can use it, and I will try to explain the concept and it might help you, and I really strongly advise you to read the book and practice the codes and run the course and see the result by yourself, and in that way you can learn the concepts. And let's get into it. Okay, this is in chapter 27 we have seen the critical section problems and how the concurrency problem in the critical section. So to avoid that critical section problems, we have solutions like locks. So let's get into it. And the basic idea of locks ensures that any critical section executes as if it were a single atomic instruction. As we have seen in our previous chapter, if you have a single atomic instruction, it would have been great, but the problem is not, okay? So in the critical section, we need to have a lock, otherwise we're going to have a problem. So an example, the canonical update of a shared variable. This was the variable we have seen, balance plus 1, and add some code around the critical section. So this is the most important thing. In the critical section, if we have a kind of lock, because when one thread is running, the other, until it finishes its execution, the other should not be enter into the critical section. So the idea is the mutex. Okay, we're gonna have lock underscore t mutex. This is some globally allocated lock. This is a mutex. Then we're gonna have the lock in the mutex, and the balance is equal to balance plus 1. Then the unlock will be, again, we're gonna have mutex. This is some kind of syntax in the book. So the basic idea, again, lock variable holds the state of the lock, okay, and available or unlocked or free. No thread holds the lock, and in the acquired or locked or hold situation, exactly one thread holds the lock and presumably is in the critical section. So once the thread is in the critical section, then it holds the critical section. So no other thread is allowed to enter. So this is two idea of critical section. And the semantics of the lock. In the semantics, we have this is the semantics lock, and we're gonna have two brackets, and try to acquire the lock. If no other thread holds the lock, the thread will acquire the lock. So this is the point. Enter the critical section. This thread is said to be the owner of the lock, and other threads are prevented from entering the critical section while the first thread that holds the lock is ended. So this is the theoretical idea of critical section problems. So the semantics is like this. And the Pthread Locks, this is a mutex, the name that the POSIX library uses for a lock, used to provide mutual exclusion between threads. This concept is very important. Mutual exclusion is very important because this is the semantics. As you can see, pthread mutex t lock. This is pthread mutex initializer. We have the initializer. Then pthread mutex lock. This one is wrapper for pthread mutex lock. After the balance, then pthread mutex unlock will be here. So this is the semantics, to hold the semantics. We may be using different locks to protect different variables. For example, increase concurrency a more fine-grained approach. This is the idea. So let's see how to build a lock then. If we know the problem of critical section and concurrency, so how we gonna avoid and how we can build a lock? Efficient locks provided mutual exclusion at a lower cost. Okay, so mutual exclusion means one thread is running, the other will not enter into the critical section. This is a shared memory problems. So building a lock needs some help from the hardware and the operating system. So this is the two ideas you have to concentrate on. So evaluating a lock, basic criteria, we have three criteria. The first one is mutual exclusion, the second one is fairness, the third one is performance. So in these three criteria we can check or evaluate the lock, okay, the performance of the lock. So the first one, mutual exclusion, means does the lock work preventing multiple threads from entering a critical section? This is a basic question. So the lock should answer this question. While one thread is running in the shared memory, no other thread is allowed to enter. Fairness, does each thread contending for the lock get a fair shot at acquiring it once it is free? This is also avoiding the starvation problem. And the third one is performance, the time overhead added by using the lock. So these are 3 points: mutual exclusion, fairness, and performance. So let's see the first step. Method 1 to implement lock. This is controlling interrupts. If you remember in our first chapter, the processor should get a haphazard. I mean, it should control, gain the processing power. Otherwise, if one process get the processor and the CPU, and if it run forever, then the operating system doesn't have any part. So one of the controlling mechanism was the interrupt. Interrupt will come, then the operating system will control over again the operating system, the processor, and it will assign another process through the short-term memory. So that is the idea here. So disable interrupts for critical section. This is controlling interrupt, means if we disable interrupt for the critical sections, one of the earliest solutions used to prevent mutual exclusion was disabling the interrupt. So invented for single processor system, example STI and CLI instructions in the x86 operating system type. That this is the syntax: void lock, then disable interrupts, then void unlock, enable interrupt. And this is the simple syntax which we can use in the x86 operating system. But the problem is I require too much trust in the applications, and greedy or malicious programs could manipulate the process. Again, I hope you remember this point, because if you trust the program that it will run for some time in the CPU, then it will preempt from the CPU, and you're gonna give chance for other processes. But what if the process will not stop running in the processor? So you cannot trust the process, okay? So this is the monopolizing the processor is one of the problem. The second one is do not work on multi-processors. And the third problem is code that masks or unmasks interrupts be executed slowly by modern CPUs. So these 3 points are the problem of disabling the interrupt. The second approach, why hardware support needed? If instead of hardware, why don't you use software support? So the first attempt, using a flag denoting whether the lock is held or not. This is the code below has a problem. Let's see what is the problem. For example, this syntax type, we're gonna have type definition and structure, lock t, then integer, we're gonna have a flag, then lock underscore t, then we're gonna have a void function here, void int, then lock t, then we're gonna have a mutex. This is going to be 0. This means lock is available. Then 1 means it is held. Mutex flag, if it is 0, then the void lock t mutex, then this we're gonna have a while function here. While mutex flag into 1, test the flag, then spine wait, do nothing, then the mutex is going to flag 1. Now set it 1. So void unlock lock underscore t, and we're gonna have mutex, and then the mutex flag 0. If it is 0, as usual, lock is available and 1 is held. This is the first attempt using the flag, denoting whether the lock is held or not. Then problem 1 of this code, is no mutual exclusion. This is the first one. Assume flag 0 to begin. So as you can see, we're gonna have thread 1 and thread 2 here. So the call lock while flag is equal to 1, then interrupt. If the interrupt comes, switch to thread 2 while the flag is 1. What is flag 1? 1 is already held. So again thread 2 comes, so this will call again lock, then the while flag is 1, then interrupt come again, switch to thread 1, then flag is equal to 1, set flag to 1, 2. So it's going to be a problem. Problem 2 is spin waiting, wastes time waiting for another thread. This is another concept. So we need an atomic instruction supported by hardware. Test and set instruction, also known as atomic exchange. This is another solution we're gonna see. So this is a simple code. We say test and set atomic exchange. So an instruction to support the creation of simple lock. Let's see the syntax. I have the code and we're gonna run it in the Ubuntu Linux operating system, and we're gonna see the result as well. So the syntax is int test and set, then we're gonna have integer here, then we're gonna have a pointer, int new, this is the syntax, then again int old, this is going to have the pointer value here, fetch old value at the pointer, and the pointer is equal to new, store new into the pointer, and return old, return the old value. So here return testing old value pointer to by the pointer, simultaneously update setting said value to the new one. This sequence of operations is performed atomically, and then a simple test and set it will continue. So as we have seen here, we have type definition, then structure, lock t, then int flag, and we're going to have void initial lock t, and we will have lock here. 0 indicates that the lock is available, and 1 that is held. So the lock flag, we have 0 here, void lock, and the lock t, and we have the lock here, while test and set. So the lock flag will be 1, then spine wait here, then void unlock, and lock t, and we have the lock, and as you have seen. So to work correctly on a single processor, it requires a preemptive scheduler, and when we run the code we will understand what I mean. So okay, let me the Unix operating system. So this is the code. So you can download the code from its free source. And what we are going to do, let me open in the terminal. Okay, this is our terminal. Let's see the direct. So as you can see, we have all these files. This is producer consumer problem, and we have producer consumer race problem, and we have also compare and swap. We will come up in a minute. I will show you. But what I want to do, if you want to see, you can see, but the first thing I want to show you is producer consumer race. Okay, this is what so let's GCC, then producer race alpha file. We have alpha file, and we have also producer race C file. What we do, we are going to Pthread. Okay, we're gonna do Pthread, and let's run it. Okay, so now Pthread alpha file. This is the Pthread alpha file. Paste it and run it. So as you can see, the final value is 0, but for sure we have critical section problem. So let me run it again. Producer consumer race problem. You see, we're gonna have counter final is 1. And again, you can run it. Paste 0 now. You see, again, executed, compile it in the. This is 0 now. So sometimes you can get 0, sometimes you can get 1, but for sure, as you can see, we have 0, 1, 2, 3, 4, okay, in our section. But as I have demonstrated here, how do we solve this race problem? Because we have race problem now. There is no lock, there is no nothing. So if I open the code, let me open the code, this producer consumer race. Let me open the code. So as you can see, this is the whole code. You can download it, but so the first one is solution to producer consumer problem using counter to be able to use all slots in the buffers suffers from race condition. So let's see, the buffer size is 5, for example, and we have 10,000. So the void producer and consumer we have here, shared by the producer and consumer thread, and the next free position int is equal to 0, and the first full position out is equal to 0. Though the counter to hold the total number of elements, and we use this in order to fill all slots. And we have integer count start from 0, and we have the main function here, and counter, and the join function, and the create function, and we have the producer as well. So please go through and see it, but this is the producer function, and we have the consumer function. So you can study the code, and it is free. But what I want to show you is that, as we have seen here, we have the problem. Okay, we have the problem. So the race problem, how we're gonna solve the race problem? We have another code. Okay, we have another code. Let me show you that. So before I go to there, yes, as you can see, we have here the TAS, producer consumer TAS file. We can compile that. So okay, let me compile GCC and This is it all. Then producer consumer test alpha file. This one, producer consumer test alpha file, copy. We can paste it here. And producer consumer test.c file. This is C file, and paste it. Then we're gonna Pthread. Okay. To compile, we have to use Pthread. So let me okay, now let me compile the producer, this one, alpha file. Okay, paste it. You can see now it is 0. So sorry. So producer consumer alpha file, this is 0, you see. Paste. So now we resolve the problem. But in the first one, if you see in the producer res alpha, we can see the files. If you see this one, producer consumer res alpha file, in this situation we had a problem. Maybe we can wait, but it will take much time. But that is Ctrl+C to go out. So in this demonstration, what I showed you is that we solved the problem. Okay, we solved the problem of critical section, and we use producer con this file. Okay, test file, yeah, this one what we use, producer consumer. This is the file we use. Okay, so go through the code, what it does, and in the global okay, definition, everything is here. Yeah, and we have also unassigned long log 0, and that is how the code works. Okay, let's continue now. The code is free. I recommend you to run it and check it by yourself. So evaluating spin locks. The first one is the correctness. For example, it is correct or not, as we have seen now in the demonstration. It is correct, yes, because it works. Yeah, the spin lock only allows a single thread to enter the critical section. How many times we run it, we get 0. 0 means there is no critical section problem. The fairness, no. Spin locks don't provide any fairness guarantee, and indeed a thread spanning may span forever. That is a problem. In the performance, in the single CPU, performance overhead can be quite painful. Example, if thread holds the lock is preempted while in a critical section, other thread scheduled will just be running on the spine code. If the number of threads roughly equals the number of CPUs, the spine locks work reasonably well. Example, if a thread waiting on a lock is on a different CPU than the thread currently holding the lock, then no issue is if critical section is short. So these are some of the ideas. So let's see another tactic. For example, compare and swap. What it does is this tests whether the value at the address pointer is equal to expected. So what does it mean? If so, update the memory location pointed to by pointer with a new value. In either case, return the actual value at that memory location. So this is the syntax. We have int, compare and swap. Then we're gonna have integer and pointer. Then the integer expected is here. Then the integer new is here. So int actual is equal to the pointer, and if actual is equal to expected, then the pointer will change by new. And then the result will be return actual. This one is compare and swap hardware atomic instruction. This is C step. Then the void lock t, again we have another syntax here. While the compare and swap, this log will flag into 0 or 1. Then if it is 1, it will spin. So spin log with compare and swap. This is the syntax. Again, compare and swap. This is C callable x86 version of compare and swap. This is a formula. I hope I have the code. Okay, we have the code. Let me open the Unix again. We have, let me demonstrate it very quickly. What we do, just use ls to check the files, and which we are going to use is compare and swap. Okay, compare and swap 1. So this one is what we are going to use. So let's discuss what this code does. For example, you have to have solution to producer and consumer problem using a counter to be able to use all slots in the buffer suffers from a race condition. So the code is the same, but what is the difference here? We have void producer function, prototype functions, and we have consumer functions, and shared by the producer and the consumer thread. So we have a buffer, and the buffer size is here. So we have integer, so next free position will be checked, and out 0, this is the first full position. So the counter to hold the total number of elements, we use this in order to fill all the slots. So what it does is, int the counter is set to 0 first, then unassigned lock will be 0 at this position. Then static inline unassigned long, then this formula compare and swap will be here. Okay. Then as you can see here in the x86, we have unassigned long, and this is CMP compare and swap, and we have this one. Then in the main function, all the same. As you can see, the main function is the same. Then the producer is here, and the consumer we have here. So the only thing, the difference between the first code and this one is we have log here. The critical section, the counter when go down, decreased, then the log is here. And the most important thing I want to show you in this code is the, where is it? Yeah, this code. This code is the syntax. Okay, so this is the code. Okay, now let's compile it as usual. What we are going to do, gcc and o, then what we are going to do, we can use compare and swap 1. Okay, in this time we use 1 because I update the code here. This one and oh, sorry. This one we have to copy this. Don't miss. Copy, paste. Then we have also compare and swap 1 c.c file. Okay. Then paste it. Then we have pthread. Okay, I hope it will work. Let's check it. Pthread. Okay, then what we have to do, let's compile it now. Let's compile the alpha file. Compare and swap alpha file, copy, paste. Okay, you see the counter is 0. Paste. Now even million times if you run this code, the result will be 0, because now we don't have any critical section problem. Like this, you see. If you continue like this, we will not face any problem. So in that way, compare and swap syntax resolve the issue of the solution, okay, the problem, the race problem. We can solve the problem like that. I hope it was helpful. So the next type is lock, linked and store conditions. So this is another solution. So lock, linked, int, we have the pointer here and return, and as you can see we have int and store conditional, and we have a pointer and integer value. If no one has updated the pointer since the load linked to this address, then the pointer will be the value, and return 1, this is success, and return 0 if it is fail to update. So the store conditional only succeeds if no intermittent store to the address has taken place. And success means return 1 and update the value at pointer to a value. This is a pointer in the value. And fail, the value of the pointer is not updated and 0 is returned. So this is also the link. This is the load link and the store condition, and this will continue. So as you can see, we have the void lock and lock t. We have the lock while the load link flag 1, this means spin until it is 0. And if the store conditional, the lock flag is 1, that means return if set it to 1 was a success, all done, otherwise try it all over again. And finally void unlock, then lock t and the flag will be 0. That is the syntax. And again we have void lock, and as you can see load linked and flag. So store conditional, then the flag will be 1. If the flag is v1, then it will spine. That is the code. The other code is fetch and add. This is atomically increment a value while returning the old value at a particular address. So what does this mean? This is int fetch and add. Int, we're gonna have the pointer value here. So int old, then we have the pointer, then the pointer is equal to old plus 1. Then if this is the case, then return old. This is how the atomically increment a value while returning the old value at a particular address. So remember, this one will return the old always. Ticket log. This ticket log can be built with fetch and add, but ensure progress for all threads, okay? Fairness. The fairness is very important. And this is a syntax as well. So we have type, definition, structure. So we have lock t. Again, as you can see, we have int. So ticket, then int turn, and void lock, int, lock t. Then lock ticket is equal to 0 and lock turn is equal to 0, void lock and int my turn is equal to feature in the add, and while lock turn and spine here, then unlock, then lock under t is equal to lock and feature in the add. So this is the syntax. So much spinning until now. As we have seen, we have a lot of methods. So hardware-based spin locks are simple and work. In some cases, the solutions can be quite inefficient. Anytime a thread gets caught spinning, it wastes an entire time slice doing nothing but checking a value. So how to avoid spinning? We will need operating support too. A simple approach, just yield. Yield means when you are going to spin, give up the CPU to another thread. So when you are going to spin, you have to give up the CPU to another thread. This is a simple concept. Operating system call moves the caller from the running state to the ready state. As you can see, it will change the state. And the cost of the context switch can be substantial, and the starvation problem still exists in this kind of situation. So the simple code, and while you are in yield, give up the CPU and unlock flag 0. So this is a simple idea of a simple approach, just yield. The sleeping instead of spinning, this is another approach. Sleeping, okay, instead of spinning. So we have a queue to keep track of which threads are waiting to enter the lock. And we have park, okay, this is in the Unix operating system. Put a calling thread sleep. Then we have also unpark, this is a thread ID, and walk a particular thread as designed by a thread ID, okay, thread ID. So using queues, sleeping instead of spinning, we have this syntax. We can go through and see what it does. Acquiring guard locked by spinning, lock is required, and park, we have also park here, okay. So the lock with queue, testing the set, yield, and wake ups, okay. These are the issue. So using queues, sleeping instead of spinning, this is the continuation of the code, and I really advise you to go to the book and you can see line by line what it does and how it works. You can find it in the book, and everything is written here. And the other one is wake up and waiting grace. Wake up and waiting grace. In case of releasing the lock, thread A just before the call to park, thread B, then thread B would sleep forever. This is the idea. Solarix solves this problem by adding a thread system call set park. By calling this routine, a thread can indicate it is about to park. If it happens to be interrupted and another thread calls on park before park is actually called, the subsequent park return immediately instead of sleeping. So this is the syntax, queue, add, and get tied, and we have the set park and the guard. So the code modification instead of the lock. Then the other one is this Futex, again in the Linux provides a footex is similar to the SolarX Spark and Unpack. Footex wait address expected, put the calling thread to sleep. If the value at address is not equal to expected, the call returns immediately. Then footex wake one thread that is waiting on the queue. So this is a syntax. Okay, so footex we have seen snipped from low-level lock in the NPTL library. So the high bit of the integer v track whether the lock is held or not, okay? And all the other bits, the number of waiters. So we can see here, this is the syntax. You can download it. It's free as usual, so you can play around. So as you can see here, we have mutex lock, and this is bit 31 was clear. We got the mutex. This is the fast pass, and as you can see, we have automatic bit test set. So the mutex is 31, and the return automatic increment mutex, and while one, if automatic bit test set mutex 31, this is equal to 0, then the automatic decrement mutex return. So as you can see here, we have to wait now. First, make sure the footex value we are monitoring is truly negative. So say that it is locked, so v is equal to mutex. So this is Linux-based footex lock. It continues if v is greater than or equal to 0, then continue. And we have the footex wait. So mutex v. Then void mutex unlock. Then we have integer mutex. As you can see here, adding this to the counter results in 0 if and only if there are not other interested threads. If automatic add 0 mutex 0 times this number, it will return. There are other threads waiting for this mutex and wake one of them up. Then footex wake is equal to mutex. So that was it. And the last one is two-phase lock. We have also two-phase lock. This is also the concept in the book. And the idea is a two-phase lock realize that spinning can be useful if the lock is about to be released. This is the idea. So the first phase, the lock spins for a while, hoping that it can acquire the lock. And if the lock is not acquired during the first spin phase, a second phase is entered. And in the second phase, the caller is put to sleep. Then the caller is only waken up when the lock becomes free later. So this is, I hope this is the last concept. And this lecture slide set was initially developed by the operating system course in computer science at Nanyang University and used by for educational purpose for Halo Academy. So this is a lecture slide set is for OSTP book written by Remzi and Andrea at University of Wisconsin. And so in the nutshell, I hope this slide gives you some idea the issue of shared memory. and the type of software-based and hardware-based systems to overcome the problem. Okay, to overcome the problem. So we have seen all these sleeping nerve spinning, and just yield concept, and we see ticket logs and feature and add and load linked and store conditional. And we have seen also the Linux course. Compare and swap is another concept. Compare and swap and evaluating spin logs. And we have seen the course also. And the problem for race problem in the shared memory is very important. So the producer and consumer concept in the shared memory area, that is a huge problem. So we try to use log implementations and a simple spin log using test and set. And test and set, we have seen all these concepts, why hardware support needed, and approaches. Second approach, this is the first approach. Why would you control the interrupt, disable the interrupt, and evaluating logs and basic criteria, mutual exclusive, fairness, performance, and building a log, Pthread Locks, the concept of mutex, and the semantics of the mutex, the basics idea. And in a nutshell, I hope this video will give you, it will help you to understand this chapter, because instead of simply reading, just we have seen that each point, the concept, it will give you an idea how to process. So I really encourage you to download the software, the codes. It's free, and the books as well, and you can play around. And I hope it was helpful. Thank you so much for your time, and we shall meet in the next chapter. This is Engineer Selassie from Blue Academy Brain Boosters. Thank you. Bye bye.